Assalamu alaikum. Good morning, everyone, colleague, and esteemed conference participant. Today, I'm delighted to present our research project entitled Exploring CNN-based Deep Learning for Audio Classification Using Air Quality Sensor Dataset, bridging the gap between two important fields: indoor air quality monitoring and activity recognition. This project is presented by the two authors, Berkani Mohamed, Rafik, Aymene, PhD student at the University Yahya Fares of Media, and Ammar Shushen, associate teacher at University Yahya Fares of Media, is my supervisor. The plan, it was first the introduction, problematic, pipeline of the system, deep learning model, result discussion, and conclusion. Introduction. The monitoring of air quality is critical importance in ensuring a healthy and safety environment in indoor space, such as house, office, and public buildings, and some indoor public space. Activity recognition has garnered significant attention due to its wide-ranging application in various domains such as healthcare, robotics, surveillance, and the human-computer interaction. Our problematic here. In most of indoor space and buildings, there is a problem of presence of toxic gases and smokes during different activities of daily living, such as cleaning, cooking, or smoking. That's why we propose our solution to solve this problem. We were offered our research projects, which consist in creating a smart system for detecting different indoor activities by intelligent analysis of measurement features of gas sensor. Develop this smart system will be capable of automatically detecting and classifying activities of daily living using air quality dataset based on CNN one-dimensional networks. Here we present our pipeline system. The first of our system, we use available dataset, and to record this, the owner of this dataset use some sensors to record it. Use 5 sensors from MQ family and 1 sensor of MG family. This output of this sensor give us some value. It will be recorded in array and save it as CSV file. We use this file. First, we're preparing the data. The next step, reshape the data to be adapted with our model. Data decomposition in 3 sets: train, validation, and test. Train and validation will be used in the training of model. Evaluate our model and save the best model during the training phase and use it to predict and test it in the final phase of test. In the first, the preparing data set for training of our model. Reshape the data set and convert it into suitable input format such as 2-dimensional array. Each reshaped data instance represented as a vector with 6 value the shape will be 6,1 to be adapted for our model for the training, and the vector is like illustrated here, like this, and this value is the measurement parameters of gas sensor. Now for the data decomposition or splitting the data, will be split into 3 sets. The first set, it contains 75% for train and 15% for validation, and this data is prepared for split it for training our model, and the remaining 10% of the data will be for the final test phase. This 10% that are not further exploited by our model during the training phase. Here, our model presented here. Like we see, we use one convolutional layer, one dimension layer with a ReLU activation function, and one batch normalization layer, and fully connected layer contain two layers, two dense layers using ReLU activation function, and one layer of dropout with 0.4, and the last fully connected layer, it will dense with the softmax activation layer. Some of methods that we use the model checkpoint to save the model with the highest accuracy achieved, to have only the most accurate model, the best trained model, to use in the testing phase and evaluated. This we use by comparing the accuracy of each epoch and have the best model that have the highest accuracy. Now we talk about our dataset. The specific parameters for measuring gas concentration to identify activities in indoor space was obtained from the database Air Quality Dataset for Ideal Classification. It is available in the website. Our dataset contains 1,845 samples, and we can say instance. Each sample has 6 sensor output value, Our dataset is decomposed as 4 situations or 4 activities: normal situation, clean air, resting or studying; preparing meal, like cooking; presence of smoke, like smoking or something like that; cleaning, like use detergents. And here we represent the dataset distribution, and like we see that our dataset is imbalanced. And now this slide illustrates a graphical representation of the accuracy and loss metrics for both the training and validation sets as a function of epoch number. We observe that the training and the validation accuracy have proportional increase with the epoch number, indicating an improvement in the model's ability to correctly classify instances. Conversely, the loss metrics show an inversely proportional decrease with the epoch number. This result suggests that the model effectively learns and adapts its parameter to minimize error. And now here we present the result of the best model during the training phase. We have in the training the accuracy of training 98%, and the accuracy for validation we have 97%. And when we talk about the loss, we have 0.05%, and for validation loss we have 0.14%. The result of this highly accurate, it was in this table, like we talked. And for the classification report, the classification report includes multiple metrics that offer valuable insight into the overall performance of the models. These metrics include precision, recall, F1 score, and support. The support is the number of samples in each class. After analyzing of the classification report, we have observation can be made of the first and second class. For the first class, normal situation, the accuracy or precision is is reported as 95%, indicating relatively lower accuracy rate compared to the other classes. This suggests that the model may encounter challenge in accurately classifying instances to the normal situation class. Regarding the second class preparing meal, the recall is reported as 91%, implying that the model may misclassify or overlook instances from this class. The F1 scores for the first class normal situation and second class preparing meal are reported as 97% and 95% respectively. The FN score provides consolidated assessment of the model's performance considering both precision and recall. Here we can propose a hypothesis, that is, maybe there is similarities between the measurement parameters of the first class and the second class, and this can be also with the last class. Now we illustrate in this slide the confusion matrix. Confusion matrix is an important tool for evaluating the performance of classification model, including deep model. Based to the analysis that we see, there is 5% from the first class is misclassified as a preparing meal, and we can see that there is also 3% from the last class classified as second class preparing meal. This will validate this confusion matrix, validate our hypothesis that there is similarities between measurement parameters of the first class and the second class, and with also with the last class and the second class. And here we represent the result of the final test with our model. We have 97% accuracy, and the loss we have 0.15%, and about the prediction time for one samples we have 41 milliseconds. And here the confusion matrix for the final test. We see that there is 3% from the first class classified as second class, misclassification of this 3%, and also 2% from the second class classified as first class, and also there is 5% from the last class classified as the second class. This also validates our hypothesis. This similarity contributes to misclassification, resulting in confusion between these three classes. Here, the comparison of the comparison with the state of the art. The performance of the proposed CNN one-dimensional model is compared with the recent related work in this slide. This comparison demonstrates the effectiveness and the reliability of our proposed approach. Accuracy, model size, and prediction time are prediction time provided are compared. It's worth noting that we were able to significantly improve the accuracy of the CNN one-dimensional model and reduce the prediction time. The best results were achieved with KNN and the random forest, which achieved accuracy of 96.32% and 96.19% respectively. In contrast, the proposed CNN one-dimensional model achieved an accuracy of 97% and the prediction time of 41 milliseconds. This will give us that our proposed model have best result than the other related work. Conclusion: the proposed smart system was tested by parameters for measuring that are not further exploited by our model. The remaining 10% of data set. The result of the prediction led us to conclude that the type of activity in space, in indoor space or house, give us best result. The test provided conclusive result in terms of classification, accuracy, detection, and prediction time. And thanks for your attention.